Like to share the slides. You can do it now if you'd like.
My slides.
Your slides. Yeah, it can be your slides. No worries. I will do mine from my laptop.
Oh, so you're not showing your NCV? You could share your screen.
This is not.
This is not. Oh, but if you share your screen,
But it's not working. Oh, okay. Let's try to do it now.
okay.
Okay.
Where's my mouse? Okay.
Okay. Hi there. Sorry, I didn't see you. We were here busy setting up things.
Now we know how it works for Linux. You're running a Mac, aren't you?
I run the Mac.
Okay. So
It's not okay.
Exercise.
I think it's about time. So, good morning, everyone. First of all, welcome to you all to the 13th European Summer School in Information Retrieval in Lisbon. So it's a great pleasure to have you all here. So this summer school has a long history. So it started in 1990. And then the first two editions were 5 years apart, but then as web search became a commodity, it started to become a biannual event. And so since, if I'm not mistaken, 2003, we had always the summer school every 2 years. So this is the first time that it comes to Portugal. The last time it was 2019, but unfortunately COVID hit us all in 2020. So the European Summer School in 2020 was supposed to be here in Lisbon as well, in particular in the rectorship building of the University of Nova University of Lisbon. And so I'm proud that Bruno and myself and some other colleagues, we were the first to host an information retrieval conference 100% online. So this was a big adventure. It happened, so the lockdown happened exactly 1 month before the beginning of the summer school, of the conference. And so what it meant is that ESSIR is now back. So this is the next event in information retrieval that happens now physically in Lisbon. So after 1 year of absence, the summer school should have happened in 21. We're back in 2022. And the scientific program, we are very, very happy and very proud of the scientific program that we prepared for you. I hope that you will enjoy it and take the maximum out of it. And last but not least, we were able to offer a very low cost registration fee to all students. So I think this was the lowest registration fee that we have in the last, I don't know, 20 years or so for ESSIR. And this is also thanks to all our sponsors, in particular ESSIR2020, Nova University and University of Lisbon, which Bruno is part of. So the conference was organized by myself, Bruno, and Pablo. I need to thank FDA symposium organizers, Ingo and Heiming, and the local organizers as well. So Diogo Silva, which you contacted to arrange the travels, you contacted for many other situations. So this is an overview of all of you. So the demographics of people that are attending the summer school. So not surprisingly, most people come from Portugal, which is normal. Second place, we have Italy. Then we have a surprise, South Korea, and I think this is because we tried to make this together with SIGIR. So SIGIR last week was in Madrid. This year you have the summer school in information retrieval here in Lisbon. And so I think this explains why we have so many people in comparison from South Korea. So also from Australia. So I'm here highlighting people from the other side of the world. So we will have breaks downstairs in the ground floor. The coffee break will be at 10:30. You will have 30 minutes to have a coffee, to get some refreshments and talk to one another. So this is the idea. This is the whole point of having the summer school in person, so that you talk to one another. So we've been locked for far too long. So use this opportunity. You can go to the garden of the campus and enjoy there outside. The buffet will be the buffet lunch will be half an hour as well. As well, in the sense it will be long enough for you to network. So the banquet will be in Casa do Alentejo, so it will be downtown. You will have to get on the subway, but it's also very easy to walk from Avenida da República, which is the big avenue that is in that direction, and then Avenida Liberdade. You can talk to one of the organizers or people with this T-shirt, and we can let you know how you can easily walk to downtown to this to Casa do Alentejo. So the plan for this week. So I'm not going to be very exhaustive, but the plan for this week is that today we're going to start with the foundations. So Professor Norbert Fuch is here for the talk of this morning, and Professor Nicola Ferro is here for the talk in the afternoon. So this is the plan for today. Tomorrow we're going to look at IR extensions like user models and interactive IR, recommender systems in the morning, and then in the afternoon we'll look at the intersections between IR, data mining, machine learning, and NLP. This is the plan for Tuesday, and for Wednesday it will be a different day, in the sense that in the morning we will have the traditional lectures, neural IR. So you will have two lectures that have been working quite intensively in these two topics. So neural re-ranking methods, Andrew Yates and Niels Reimers. And then in the afternoon on Wednesday, we'll have the doctoral symposium, or the FDA symposium, which is a kind of a doctoral symposium. And we've sent you yesterday an email suggesting that if you have this interest in discussing your ideas. So use this afternoon to make it a more structured discussions with potential lecturers and also the FDA organizers. So they will be here, talk to Ingo or Jaime, and they will arrange a lecture for you to talk about your research. Okay, so the Wednesday afternoon is reserved for that. On Thursday, we're going to have again very specific lectures. So information retrieval for medical applications, conversational search. This will be in the morning. In the afternoon, multimedia retrieval, and to close the day, we'll have bias and search recommender systems. Okay. Then to close the day, not the day, sorry. To close the summer school, we'll have this final lecture about fairness and interpretability. So it's a very hot topic nowadays. And last but not least, this is a panel which we thought that you would like to discuss with more senior researchers, which is how to transition from a PhD in first year PhD to close the PhD, and then after the closing of the PhD, what careers lies ahead of you. Okay, so I think this is a very nice panel to have in the summer school, where you are supposedly at the beginning of your research career, so you're probably first, second year student of a PhD, and so you have a lot of questions, a lot of anxieties, and also questions about what to do afterwards. And so this will be a nice opportunity to poke the panelists and get answers out of that. Okay. And then the afternoon is free on Friday. Okay. So now this is the introduction I wanted to say. Thank you all once again for being here, and I'm now going to transition to the first talk of the morning. So this is a very important moment for me. I'm going to present Professor Norbert Fuhr. So Professor Norbert Fuhr, he has been a full professor since 2001 or two, if I'm not mistaken. Okay. Professor Norbert Fuhr is one of the big minds, one of the founding fathers of information retrieval in Europe, together with Keith van Rijsberg. Professor Norbert Fuhr is one of the few Gerald Salton awardees. So it's an award that is given only every 3 years by the ACM-CIR interest group. So, and this award was made for the foundations, for the contribution to the foundations of information retrieval. And so it's an honor to have Norbert here this morning with us, sharing his knowledge and wisdom with all of us. So thank you very much.
Thank you,
Norbert, the Zoom is yours.
Okay.
The Zoom and the floor is yours.
Try. You first have to stop sharing your screen.
Sure, I will do it. So the lectures are also being broadcasted on YouTube. But there's no possibility for people to interact and ask questions with the speaker. Okay, so it's only one way, of course.
Okay. Good morning, everybody. So I'm here to give you introduction into information retrieval. And of course, introduction is always difficult what do you include, what not. So I decided to focus on some concepts which I think are important, but then there's also additional material in certain areas. So in principle, I'm flexible. I don't have to present everything. And especially, I'm very open to questions. So whenever you feel the need, please ask questions to make this a bit more interactive, because some of the points are also very subjective, as everyone also looked at some of the older introductions into IR. Each of the presenters has his or her specific topics, and so just regard this as a very subjective view. So first I will start with some examples, and then I will address the question, what is actually information retrieval? You probably think you know what information retrieval is, so we will come to that and we will hear what it is. So first let's start with some examples. So we all know about web search. Then of course we all know about product search, where information retrieval plays an important role, but was a recommender systems as well. Then we have intranet search, so on one hand meaning the websites internal to institutions. Another important variant of that is enterprise search, searching all documents within an institution, especially for a company, for example, where you have rather heterogeneous sources and types of documents and rich metadata and access restrictions. So commercially, that's a very important application. But of course, it's very difficult to do research in this area because you just can't get access to data from this area. So that makes it a bit difficult, but economically, it's a very important application. Then, of course, we have digital libraries. That's another important application. Then multimedia, searching for images. So Portuguese wine. Yesterday I was at Portuguese wine tasting, which you can do here in the city. Then, of course, video. You all know about video. And if you have the opportunity, you should go to Fado Place during this week. Typical Portuguese music. Then we have recommender systems. I will not talk further about recommender systems, but just express that they can be regarded as part of information retrieval, meaning that it deals with finding without actually querying, whereas we in IR normally assume that there is a query at the beginning. So from these different applications, we can derive certain facets of search that can be addressed. So language is an important point that's often ignored. So most research deals with English or just one specific language. That's my language and that's it. But there has been also rich research on cross-lingual IR, so originally mainly in Europe, so CLE, Cross-Language Evaluation Forum, the European Evaluation Initiative was very strong in this, but research-wise, cross-language retrieval, at least in Europe, is more or less solved, so there's little more activity. Unfortunately, there's hardly any real applications for this. So Google had a better version where you could do cross-language search, but this is no longer available. Then structure is another important point, which unfortunately also is not supported in any systems that I know of. So in the 20 years, we had the INEX initiative dealing with XML retrieval hierarchy documents. The idea is that when you search for documents, it not only gives you the document, for example, the system returns you a thesis of 150 pages, then all you are left with is string search in the PDF. This is not the solution. So here we address the problem of finding the relevant passages within the document. So here it shows the hierarchic structure. You could click on the parts that the system deems relevant, and then here you see the relevant parts. So that's also still research-wise, that's more or less solved, but it hasn't gone into the application. Okay, media, we all know about. Most media search is based on text, but then there are also systems that allow really searching for similar media. Google now also supports image similarity search. Then there are specialized systems focusing on certain types of objects, like for example, people or product search. You have price comparison websites, so that's product search in principle. That means different types of objects, and the system is able to distinguish the different types and just focuses on one type. In recent years, knowledge graphs have become important. So instead of searching for text, the system tries to find the knowledge in the form of facts or whatever. So you all know this from Google. On the right hand of the search result page, you have this knowledge graph information, and here we have Wikidata. That's the underlying knowledge. So Google also started from a kind of knowledge graph that was collected by a community, and they extended it commercially. So the community effort nowadays is mainly Wikidata, which is derived mainly from Wikipedia by information extraction methods. And here is, for example, the knowledge graph browser from Iago. They extracted this from Wikipedia, where you could start here with Albert Einstein, and the underlying model is RDF. So you have triples, subject, predicate, object. So Albert Einstein lives in Germany, or has won prize, Nobel Prize physics, and so on. And then they had this browser. Unfortunately, it's no longer available. Well, 2007, that's ages in terms of computer science. And then you could click on one of the labels, and so here he was born in Ulm. Here, and if you click on Ulm, the city where he was born, then you can see other links originating or ending in this node. And currently there are many efforts building upon these knowledge graphs. How can this knowledge be exploited for improving your search results? Then we have question answering. It's popular since the mid-90s. So you can not only can search for facts, so who is the current president of the USA. I tried this also with the EU, but Google wasn't able to tell me the answer. And besides facts, nowadays also systems are able to give instructions. So Google, for example, has how-tos, so short how-tos. How do I delete my Instagram account and get a list of list of bullet points or steps to follow. And yeah, then recent years argument retrieval has become very popular. That is when you have to decide a question, for example, should I get a vaccination or not? What are the pros and cons? Then there are attempts to automatically extract pros and cons arguments from the text, and currently the systems, they do so. So if you read carefully the text on this slide, and you will notice, well, the division into pro and cons is not really proper. So the systems, there's still more work needed to really do good argument retrieval. And this is ongoing research, research teams. And yeah, finally, of course, you can also distinguish between more static and more dynamic content. So traditionally, it was assumed you have to have a static database, which is updated once a week or so at most. But nowadays, you have highly dynamic content, and this means that you need appropriate methods for dealing with the high dynamicity. Maybe so Twitter is the most popular example, but if you look at their retrieval functionality, then it's very limited. It's just string search and not real information retrieval what they offer. So that's the challenge doing efficient search in highly dynamic content from information retrieval point. And finally, so to sum up for these facets that are named, we can distinguish language. You can have monolingual retrieval, that's a standard case. Then cross-lingual retrieval, formulating query in language A and searching for documents in language B, or multilingual, searching in parallel for all languages that are in the corpus. Then you have the structure. Normally you just assume that you have an atomic structure. Document is just a blob of text. Traditionally, so in reference retrieval already, you have documents separated in fields, so you can field-wise search. Then you have the tree structure, for example, in XML or any document that you write has an implicit tree structure. So if you are using LaTeX, then it's very explicit. But if you are using Word, then it's more implicit unless you are using a proper template. And then there is the graph structure, like for example, the web. And yeah, then on the media aspect, we have text, facts, images, audio, videos, you name it. Objects, there may be different types of objects, so we can search for products, for people, for companies, and so on. Knowledge graph, here we are dealing with objects and relationships. And if we go beyond objects, we are looking for answers or arguments. And yeah, then we have static versus dynamic contents for databases. And yeah, then, well, information retrieval is more than just ad hoc search. Here I looked at the Clay 2022 tracks. So Nicola will know more about the ongoing activities tracks. Because he plays a major role. I don't know, are you the head of everything or just, yeah, so. And so we have, for example, here a application in the biomedical semantic indexing and question answering. Then there's a track dealing with COVID-19. So soon after the pandemic started, then, of course, there were lots of publications from medical doctors and researchers all over the world. And the IR people, they were in the lockdown. So they thought, what can we do? Well, we could set up a collection of the COVID material, because also the need of the people for finding information was very important. And from that, so collections with tens of thousands of documents published in the meantime are available. There are different retrieval methods I investigated for this purpose. Yeah, then we have more so ERISC mainly deals with classification, so classified users, for example, whether they are suffering from anorexia or depression based on their contributions to the forum. Yeah, then here we have an identity recognition. Here we have more dealing tasks, dealing more with classification. I want to go into the details, but you see that there's a rather broad spectrum of information retrieval. So, questions so far? That leads me to my first question. What is information retrieval? From what you know already, maybe in light of these examples, there's no perfect answer. And if you put 5 IR people in one room and ask them, each of them will give you a different answer. So what's your answer? There's no wrong answer.
I would say like extracting a structured representation of a collection.
Exactly structured.
Yes.
Okay. Good. Yeah.
Very abstract.
Yeah, yeah, it has to be abstract. You will see all the definitions I show in the following are also be abstract, more or less. Other opinions?
Maybe finding relevant information. A collection of a lot of relevant and not relevant.
Yes, yes, yeah, that's more or less one of the standard explanations you can hear. Other opinions? For example, relevance. So there's database querying. So if you are querying a relational database, this also be part of information retrieval.
Find refer using text from a collection, unstructured selection.
Yes. User intent, unstructured collection. Yeah, yeah, yeah. Maybe that's it. Many people would say yes.
Yes, I would say basically finding any kind of relevant documents in large collections of data to satisfy information.
Okay.
So
Yes.
put that at the center.
Yeah, yeah. Yeah. More? Yes. Okay, so let's start. So the classical, yeah, what subjectively many people would say information retrieval is content-oriented search. So in contrast to databases, where you're just focusing on attributes, we are dealing with content-oriented search, content in media objects, and then in principle one can search at different abstraction levels. That's important because you can distinguish between syntax, document as sequence of symbols, but this is not what IR is about. That's what the database people do. Relational databases, they work at the syntactic level purely. And but then we have the semantics, that's the meaning of the text or the media object. In databases, the semantics is already in the application, maybe not in the database itself. So it's about the meaning, but then we also have the pragmatic level, and that's the usefulness for solving my current problem. That's also what was mentioned several times, the relevance. That relevance in principle refers to the pragmatic level. Does it really help me for my current problem? That's what many people would say. So for example, here I have image, and so here, as a simple example where you can say, well, syntactically, you can flash for colors, contours, pictures, and the image retrieval methods, the ones that are most widespread use, they are based on the syntactic level. They compare similarity with respect to colors, contours, and textures. That's the best match, but it's mainly syntactic. Then we have the semantic level. That means we are dealing with objects, properties, and relationships that we have. We have cars and trucks, and which car drives which one, and then properties. You have a blue truck here, for example, and so on. And that's the semantic level, but then the pragmatic level, that's task related, and that's especially in the case of images. Pragmatic level is not obvious at all. So, for example, popular application is for journalists when they have to illustrate an article, for example, about the frequent traffic jams, or that new motorway is needed to resolve that problem. Then they could use such an image, for example. That would be the task for illustrating the story. And the same thing can be done for text, but that's a bit more complicated, so I don't want to go into the details here. But the important thing that is that information retrieval is mainly about semantics and pragmatics, and not about the syntactic. If you have a system with a purely syntactic search, like for example Twitter search, that's not really what the information retrieval is about. At least according to this content-oriented view. Then next definition I would like to show is the one by Justin Sobel. He wrote an article in the SIGA forum where he said information retrieval is the study of techniques for supporting human cognition with documents using material that is sourced from large document collections. So here the user view is given more importance, and relevance also, of course, is user-oriented, and also the problem of human cognition, meaning the user has to understand the document. So, for example, if you ask a question with respect to COVID, should I get another vaccination or not? The system would return to you a medical research article discussing all the details. For most of you, this would be of little use because you are just not able to understand what's in the article, so it would not support your cognition. So that's an important point of view, that the document should fit to the users' needs and capabilities. And finally, my favorite definition, which we developed in Germany in '92. That's exactly 30 years from now. We also became a professor in computer science, where we founded this German information retrieval specialist group within the German Informatics Society, and you have to formulate a charter for your group. There we said information retrieval is about vagueness and uncertainty in interactive information systems. So these are the central concepts from our point of view. Vagueness means that the user cannot give a precise specification of her information need. That's how you recognize vagueness. This can be either observed via vague query conditions, and currently I have a PhD student who works on product search in online shops, and she's regarding laptops and clothing. And when you ask users, so imagine you need a new laptop or you need a new jacket, what they tell you that their query is very far away from the description of products in the online catalog. So from a system point of view, these descriptions are very vague. They do not specify, for example, for the laptop, precise attributes. They say lightweight laptop, mid-range price, a big screen, something like that. And it's very difficult to translate that into the attributes that are used by the system. So that's a typical case of information retrieval. So it's not a database application. That's the way how it's treated in most systems. They use underlying relational database, query in, tuples out, but that's not the solution to the problem. Users have vague information needs, and so you need appropriate support. And what we then observe is iterative query formulation. So once you press the users, but you have to specify precise attribute values, then you observe that they are playing around with the values to get what they need. So as soon as you observe that they reformulate the query over and over, this means that this is a vague information need underlying. In a traditional relational database, you know what you are searching for, and if you also know SQL, then it's straightforward to formulate a query and to get the answer you're looking for. One step. But in information retrieval, it's typical that you iteratively have to formulate your query in order to arrive at your goal, find what you're looking for. So that's one aspect. The other aspect is uncertainty, meaning that the system has uncertain knowledge about the content of the objects in the database. So this leads to an uncertain representation, and in effect it leads to wrong answers. So the system does not fully understand the content of the text. For example, when you have words with multiple meanings, then just doing word matching, this is documents that are not really what you were looking for. A simple example. And more important, the representation is always incomplete. That means the system is missing answers. So when there are synonyms for the terms you type in your query, then of course searching for all other synonyms and all other possible formulations for the same need might retrieve many more relevant documents, but these are missing because of the incomplete representation. So that's these are the two important features. So whenever you look at an interactive information system and you notice features of vagueness and or uncertainty, then that's an information retrieval problem. Even if the database people say, keep away, we solved that. As soon as you notice vagueness or uncertainty, then it's our game. We know best how to do it, or at least we think we do. Okay. Questions? Yes. Yes. That leads me to the next point. Exact. Yeah, what is relevance? So that's my question again. What would you say? What is relevance? Yeah.
It's a Greek which we usually satisfy with document.
Yes. Yeah. User satisfaction with documents. Yes. Yeah.
Maybe there is more distinction of more objective relevance and more subjective relevance. Objective how it related the document corresponds to the subject. Subjective relevance can be and depend on the user. So even if the document is objectively relevant, the user can control it for this person.
Yeah, yeah. Yeah, like for example, like my example from before with the medical document, if you don't understand the document, although it's relevant, it's objectively relevant, but subjectively not. Yeah, that would be a good example, yeah. Other, yes.
Which the results satisfy specific user.
Yes. Yeah.
Users educate or information that they are interested in.
Yes. Yeah. Other. Yeah, in the following, I will show you that relevance is rather a complex beast. So, and that in principle, yeah, there are still some interesting research problems. So first, of course, we all understand that in contrast to databases, an IR system itself, the system cannot decide if an answer is correct or not. So normally we say the user has an information need, which is originating from some kind of work task. Even if it's not work, it could be also pleasure or so, with some kind of task. And then the relevance is the relationship between the document and the information need. And in principle, yeah, it can be judged by a user or an expert. That's, yeah, the simple definition. And here we have a figure that tries to illustrate a more complex relationship. So here we have the work task, W, and here we have the assessor's or user's cognitive space. And then on one hand, you could regard the user's motivation, that would be motivational relevance, but we keep that aside. So more important is first, given the work task, we have the first transformation into the user's cognitive space. That's the cognitive perception of the work task. How you as user understand what you actually have to do. And there might be already some discrepancy between work task. For example, when your professor tells you something and you try to do it and return your result, and the professor might tell you, no, you went totally astray. So your perception of the work task was a bit wrong. Okay, your perception of the work task, and then with respect to the objects you found, that would be the situational relevant. Does the document really help you with respect to this work task? Then, of course, in most cases, you cannot just tell the system what your work task is. I had one example, how do I delete my Instagram account, where I was lucky enough to find a solution in different steps, how to do this work task. In most cases, you will not have such a how-to for your work task. Instead, you have to break down your work task into specific information needs. And then, yeah, you regard the object that you found with regard to the information need. That's the cognitive relevance. That's what normally the user would say, that's the relevance or the definitions that you've heard so far. That's the cognitive relevance. And then, of course, the system is still not really able to interpret your information need, read your mind. So you have to formulate a query. And then the system will use this query to return some object. So that's the blue arrow should be denoted by system relevance. And the relationship between the object and the query, that's a topical relevance. That's what also an expert could judge about, looking at the query and looking at the document. Is this document an answer to the query? So there are many different types of relevance involved, and you should be clear what you are talking about. So the situational relevance is related to the perceptive task, pertinence relevance is related to the information need. That's the user point of view. Then we have the intellectual topicality, or also sometimes called relevance, as judged by human observer. So given the query and the document, that the internal assessor judges about the relevance or topicality. And then we have the algorithmic relevance or system relevance. That's the system score comparing request or query with object. And yeah, I don't like this algorithmic relevance, so it should be more just the system score relevance status rate. And whereas the relevance usually is regarded either as the pertinence, so the subjective importance of the document, or the topicality, that would be the view of an external expert judging about the relevance. I just was looking at what should it be time for our coffee break now? Oh, no, my watch is still not sharp time, sorry. That's, I have a lot more time to go. Okay, sorry. Okay. And yeah, then we have aspects of relevance. So from a different angle, that's a typical definition we work with here. We just say pertinence, so the subjective relevance, it's also called sometimes, or the topicality, the objective relevance. But in principle, relevance has many different facets. So one can regard accuracy meaning that the information is accurate. Currency, that means that the information is recent. Specificity, a summary of the information is available. Reliability, that is the source is expert, professional, or experienced. Then we have accessibility, that the source is actually available when we need it. Verifiability, that the information from this source is consistent with that from other sources. Clarity, that the written or spoken language is clear and well organized, and the presentation quality, it's presented in permanent or stable form, and the presentation preference, that it has interest or entertainment value. So they did empirical studies of users and asked them, why is this document relevant? And then they came up with all these aspects. And normally, in most retrieval application, at least the additional ones, most of these aspects don't play a role. For example, when you have a news collection, then in principle, yeah, these factors do not play a big role or hardly any role, because you have a rather homogeneous collection of documents. And so there's no need to bother about these aspects. But when you are dealing with real world applications, or dealing, for example, with the web, then these aspects become very important. And the current solution on the web is just popularity, more or less. But, Google observes how many people click on which answer. Okay, these are the good ones, and they are part to the user. But the actual aspects, they are not really investigated so far. Yeah, they do fight against web spamming or so to an extent, but besides that, the problem. Yeah, so it's fight against web spam and popularity. That's how they try to solve these problems. There are many applications. These aspects play a very important role and addressed. And the question is, how can we address these aspects? And well, we had a Dachstuhl seminar some years ago, which dealt mainly with IR in social media, and we came up with the information nutrition labels as one approach for implementing relevance. The idea was that the system tries for each document to estimate the value of certain facets. So, for example, I have news articles, so to how factual is, how much facts does the document contain, how much opinion is there, in how controversial is the topic, how emotionally, how on topic is the document with respect to the theory, then the readability or reading level, how technical is the document, how authoritative is it, and how viral is the topic. And the idea was that, yeah, this should be related to information nutrition, called information nutrition labels, like normally nutrition labels that each day you should eat at most so much salt and so much fat and calories and so on. And you should only digest so much opinionated or controversial articles a day or so. That was the idea. But in principle, these aspects, they are very much related to the relevance aspects I showed on the slide before. So that could be a way for supporting the concept of relevance by just filtering documents according to these aspects and to the user according to the user profile. So this way you could find, identify those documents that are really relevant for the user. And there have been two publications on this topic. So from my own group, so we had an application called NewsScan, where we used automatic methods for estimating values for these six aspects: the source popularity, article popularity, ease of reading, sentiment, objectivity, and bias. And then you could, in principle, set the filters according to your information needs, so user-specific filtering of news. And there was another publication at about the same time from the WebList group in Weimar by Tim Gollop and others in the PhD thesis just last month. I was one of the reviewers. And yeah, that was just a side product, not really the topic of his thesis, where they identified the time, the temperature, so how viral, or whatever it means, the transparency, the volume, and the credibility of documents. And so that they showed this for each article. That was the basic idea, so similar to ours. And in principle, so there are methods available already for estimating values for these facets. So topicality, that's what IR folks have been doing since 50 years, or even more. Then readability, there's been quite some research in the last 2 decades or so. Technicality, a little bit less. Then factuality, yeah, there are also methods dealing with the virality. It's just, yeah, there are also sources where you can identify how viral a topic is. Emotion, yeah, we can know about the methods for identifying emotions in reviews. Then how to identify opinions. There are also some methods. Controversy. You can also try to identify, and of course a lot of research has been done on authority, credibility, and trust. And so, in principle, for estimate, there are automatic methods for estimating values of these aspects, but of course, there's still room for improvement, and it depends on your specific application, how you can, yeah, to what extent you can build upon existing methods of Same, are you here? No. Right. So he also works on, in the area of medical retrieval, and so he tries to find relevant information for medical doctors, and he has identified certain facets that are important to describe doctors' information needs. So yeah, that affect relevance beyond topicality. So that's, I think, is a very important direction. So if you really want to provide users with relevant material, especially in specific application, then we have to address this relevance aspect in one or another way. Information nutrition labels, or going back to the original aspects identified in the barbarian chamber, or finding other aspects that are important for your application. Then think about automatic methods for estimating the values of these methods. I think that's a very important issue, at least for many applications. It's not sufficient to just run some neural network over a test collection and hopefully all the problems are solved. You will address additional aspects to find material that your users actually need. Okay, so much about relevance. Any questions relating to relevance? Yes.
It's like a one question that is we are constantly talking about extracting documents or source documents.
Yeah.
But do you consider like a task, an NLP task, processing task as part of information retrieval? For instance, name identity recognition.
Yeah.
Would it be framed as an extraction problem?
That leads me to the next part of my talk. I won't talk much about NLP, but it's the representation problem.
I'm asking this because once I submitted the work in one of the reviews, exactly that. It's more like an NLP task, not information retrieval task. So like.
Yeah, it's always the problem, the separation. Yeah, there are people, they want to know to what extent does this really help with the retrieval problem. So you can work on better representations, but then there are people who would like to see, does this really help in search? Otherwise, it's an NLP problem. The typical attitude, I understand. So.
Also, there are always problems with figures number 2.
Say again?
Also, there are also always problems with figures.
Yeah.
I have one question.
Yes.
The previous slide, you showed different facets, and then one of them is factuality.
Yeah.
And like, there's a lot of work that people do, fact checking, that they do. They use the retrieve, like the top 10 retrieved documents, the train model, and then in this case, it would be using the same to estimate the factuality. So how can we break this cycle? If we want to put this in a nutrition label, but we're using the same documents that will be fact checked.
In the end, yeah, of course, it needs manual judgments. That you need some kind of ground truth, and that has to be done manually. There might be methods for automatically deriving some of this, like for example, in general, instead of relevance, just click-through rates and so forth, approaching it. But even the big search companies, besides looking at the click-through rates, they occupy hundreds of underpaid workers for doing manual relevance assessments. So it's hard to do without, because this understanding is limited. Other questions? So, yeah, the next part I will be very brief, but just emphasize the role of representations. You have to be aware that when you're dealing with, I will mainly focus on text, but for multimedia it's even more complex. So I won't go into multimedia, but in principle the same problems arise. So when we are dealing just with text documents, then in principle we have to distinguish between free text search that we all know, that's web search, and on the other hand you have the semantic approach, which is older historically, that is meaning that you assign semantic descriptions to documents. And well, semantic descriptions have been around since centuries, so even longer, namely in the form of classification schemes. So, so for example, hierarchy classification, some libraries. So the traditional libraries, they all are based on some classification scheme that determines where a book is placed in which shelf. Well, we once had like lazy librarian in our first university, just put books in the order they were bought. That was nice to see what new books are in, but if you were looking for books on a certain topic or so, that we were lost more or less. So that's why we need a classification. And you can still see many classification schemes now in product catalogs, for example. And also every supermarket has a classification scheme in order to determine where to place which product. And we all subjectively have some idea about the underlying classification scheme they are using, so we are able to find products we are looking for. So that's the traditional, most oldest method of semantic description. Then we have tagging has been popular, is still popular, so that means users assign tags, but that comes with lots of problems. So tagging probably creates more problems than it solves. Might be helpful when you are dealing with multimedia objects, so having tags for images instead of just a rare image certainly is of some value, but it's not a very good form of representation. And then we have ontologies. Most popular is OWL, web ontology language, and for example, the knowledge graph that was shown earlier, principle is one form of ontology. And also nowadays in product catalogs, in principle, they do not simply have a classification. In fact, they use an ontology because for each class, they have certain attributes, so that or facets. So on the left side, usually they show you then the different facets with the possible values, and this is what an underlying ontology provides you with. So ontologies, especially also with knowledge graphs, so they will be playing a major role in the next years. Just some examples. So here, for example, on the web, so there has been tradition. First there was Yahoo, but there was a commercial. So Yahoo originally was just the attempt to classify web pages. And then they turned it into a company. And then there was a public effort with Demos, called Demos, and it has been now renamed to Curly, but I don't think that it's still actively maintained any further, but you can look for Curly and still search for the web pages that it catalogs. So, yeah. I don't want to go any further into semantic descriptions, and then so go with the ontologies that are also closely related to information extraction and so on. So that's just one approach, and in principle one can also combine the two approaches. So semantic description with free text search, it always has been done in the past. And nowadays, more modern representation you can put as well, but just keep in mind that there are always two ways.
Early is really an ontology, or like a hierarchical.
No, it's more hierarchical classification. Yeah. If you want an ontology, go to Amazon, for example. There you can see. go down to one product class and you can see
there are some concurrencies across categories in DMOS and curly, right?
Yeah, no, curly is the successor of DMOS. DMOS was shut down for history. I read once, but forgot it due to some unfortunate events. DMOS was closed down, and then curly got the data and they revived it. Okay. And as I said, I don't want to go deeper into this, just always keep in mind that there are also semantic descriptions in all flavors, and especially ontologies. Here I just want to focus more on free text search, because that's what most research is dealing with. And also models are based on free text search. So first, whenever you are using free text search, you should be aware of the problems. The free text search is different from string search. That's the first and most important thing. You will notice if you just, as I said before, search for a publication and find the thesis, and now you have to search within the thesis, and all you are provided with in your PDF reader is string search. That's not information retrieval. What you are missing is, well, dealing with inflection. That is, you have for nouns and verbs, especially inflection, so computer, computers, or fly, flies, go, goes, going, and that would be inflection. Then you have derivation from the same word stem, so compute, computer, computerization, or computation. They are all based on the same word stem. You might be, when you search for computer, you might also be interested in computerization or computation or compute, but of course with the decreasing probabilities. Then you have the problem of synonyms, so a mobile or smartphone, table, bench, board, counter are examples of the way you formulate a query. And the document might contain synonyms for the popular words. The major search engines, they use synonym dictionaries to help you with that. And in most cases, they do this implicitly, but there are also operators who explicitly ask for synonyms. For example, in Google, there's a tilde. You can prefix your search term with, and you tell Google, please search also with the synonyms. But, maybe it does this also automatically, I'm not sure. It changes also from version to version. Then you have polysemes, that word with different meanings. In many languages, you have big problems with compounds, Niveau, test, but there are other languages like German, Donaudampfschifffahrtsgesellschaftskapitänsmütze, that's just one word. And the Finnish can even top this. Do you have anyone from Finland? Unfortunately not. Okay, I can say whatever I want about Finnish, or anyone know Finnish? Okay. Okay. So Finnish is even worse with compounds, so you need a way to deal with it. And then on the other hand, of course, you have phrases, especially in English, where you have only a few compounds, but many phrases. And so information retrieval and retrieval of information mean the same thing. And yeah. Anyone know how to search for phrases in Google? Yes. The put the phrase in apostrophes. Yeah. But yeah, then of course it would not find, they would find exactly information retrieval, but not retrieval of information. So that means it searches exactly for the same phrase. But if you have semantically the same phrase, then this doesn't work. So that's the problem. Still, it's not solved in many systems or current systems. They just do implicit adjacency rates. Right? Without apostrophes in your query, then the system just looks at the size of the matching window in the document. The smaller the matching window, the higher retrieval score. That's the ad hoc method. Principle one. We need to use NLP methods to do it properly, but I think it's used only in specific applications. So the methods that are mostly used, typical methods is that for inflection, derivation, stemming algorithms are used. So in research, we mostly reduce the words to the word stem, so most algorithms, whereas for the web search engines, they reduce it only to the lemma. So they only deal with inflection and do not address derivation, because derivation you get, might get very different meanings, and so they avoid derivation, and you can also not even force Google or so search for derivations. Only deal with inflection. Then synonyms, one uses synonym lexicons, compounds. There are certain splitting algorithms that work reasonably well, and for phrases, mainly does adjacency search. And well, yeah, most systems they only implement stemming, a mild form of stemming, dealing with the inflection, and adjacency search. That's what conversion systems do. Okay, when we do in information retrieval, what we do is, well, we start with objects. When we start from a document object, for example, an article. This is from Bill Cooper, who also got the Thornton Award in the mid-90s or so, and he found out that one of the basic models in IR, I later talked about the binary independence retrieval model, that the justification given, the original justification given was not quite correct, because the original justification would not have been able to explain the good results that we get from that. That was described in this article. I'm getting sidetracked. Let's get back. So, given a document, then what you do is first you take the text, of course, when you have the web. First have to remove all the HTML stuff, and so just in order to get plain text, then what's typically done is you remove stop words and do stemming, at least what you do search. So you would remove words like in, the, of, and so on, because they don't have a meaning. But you have to be careful. So when the first German search engine was set up in the medical domain, but of course the documents were in English, and they invited someone from the ministry who had given them money, and they were searching for vitamin A. And well, they got all kinds of vitamins because A is a stop word. So you have to be very careful with your stop words, because in certain contexts they might have meaning. Or when you search, for example, in Shakespeare's works, to be or not to be is a phrase consisting of stop words only. So you also will not be able to find that. So be careful with your stop words. And yeah, the other thing is stemming, that you use the words to the word stem. Okay, then given this sequence of stems, next thing is that we represent the document as a bag of words. So we drop the order. In that case, so that's in research. So if you are interested in adjacency search, then of course order remains important. But here I'm more looking at the traditional IR methods. So that is to just drop the order and count for each word, then how often does it occur in the text. So theory occurs twice, and construct occurs twice, and all the other words occur only once in this text. And then based on this representation, so it's very important, whatever application you have or you find described in the document, try to find out what's the underlying representation, how much knowledge about the document do they actually employ. When someone, for example, talks about video retrieval, oh great, but what's the representation that they actually use for search? Maybe just some text or so describing the video. That's not video retrieval, that's no great video representation. So it's always important to look at the representation. Although when I started in IR, I worked on probabilistic models, and I figured out that the probabilistic models, they all use a set of words, whereas the vector space models, they use the bag of words. So the probabilistic models, they were limited in their representation already, and no wonder that their performance was poorer than that of the vector space models. And Salton, who was leading figure in vector space models, always said, yeah, these probabilistic methods, they just don't work. You see, look at the results. We are much better than probabilistic models. Yeah. And I was able to come up with a better representation for probabilistic models, and we got better results. So it's important to look at the representations first, and you can compare two models only if they are based on the same representation. Otherwise, just say, yeah, they use separate representations, and that's the reason why they have different performance. It's not the model, it's the representation. So first make sure to have the right representation, and then you go to the description. So that is, you describe your document in some way, for example, in a simple way, just as a vector, pairs of terms with weights. So that's the description, that's what you actually use for retrieval. The representation is the knowledge that you have, and from that you derive the description you need for your retrieval model. Here we see it as in a conceptual model, how we describe the retrieval process. So we have the document here on one side and the document query formulation on the other side. Next, you derive the representations. So what's your actual representation of your document? Like, for example, the bag of words, and what's the representation of your query? It could be also just a bag of words, it could be, for example, also Boolean query formulation or whatever you like. And the query, for example, could be the original query, could be a spoken query, but then from that you derive the representation on your way to actually doing retrieval. Then the next thing is the description. So what does the description of the document look like this vector with term weights, and the description of the query, how does it look like? Is it just a set of terms, or is it a vector of weighted terms, or is it a Boolean combination of query terms? So that would be your description, and then the retrieval function compares document description with query description and returns retrieval status value. So that's the basic underlying model. And for each approach, it's really worthwhile understanding what document, how do documents and queries look like, how are they represented, and then for the model, what are the descriptions actually used for retrieval. That's important, and especially if you, many people, there has been lots of research and just playing around with trying different retrieval functions, but you always must be aware, is it just a retrieval function, the way you combine descriptions of query and document, or do they also use different representations? Now, nowadays, would be learning to rank methods and all the other machine learning methods for different tasks. They give you the possibility to use very rich representations, and that's also the reason why they perform better than classical methods. And so in these cases, you have much richer representations leading to better results. Okay. Okay, so yeah, I think we have 10 more minutes. No, yeah, no, I can do just the next part, and then. So yeah, so the retrieval function and the descriptions used, so that's part of the IR model. So that's maybe part of the models, and so yeah, just do the very first part. So it's very important. One of the few theoretic universally valid truths in information retrieval is the probability ranking principle. So many people think nowadays, well, IR is just about tuning deep learning methods and getting good results. And we have another idea which kind of network to use and how to train it, and so get some better results than I'm a great IR scientist. But IR, any science is about general statements, universally valid statements, and sometimes you can find even in IR papers formulation. Our experiments prove, well, experiments prove nothing. They can only falsify a hypothesis, but experiments prove nothing. Proof means universally valid statements. And unfortunately, in IR, there are only very few universally valid statements. And the most important one is the probability ranking principle. So that's always true. If universally valid statements have the form if A, then B. If certain conditions are fulfilled, then in the form of A, then if A, then follows B. And so the probability ranking principle is about optimum retrieval. You always want to get very retrieval, but probability ranking principle defines optimum retrieval, tells you can't get any better. That's the optimum. And it does it for probabilistic models. It means you have to rank documents according to decreasing values of the probability of relevance. So given the query and the document, the system estimates the probability of relevance. And if you rank documents according to decreasing values of the probability of relevance, then you can theoretically show that you get optimum retrieval quality. And so it means in terms of retrieval measures, you will hear more about measures this afternoon from Nicola, you will get the best values in terms of measures, and you can also alternatively look at the retrieval costs, defining costs for relevant and non-relevant documents. Then you get minimum retrieval costs. So the probability ranking principle was originally formulated by Steve Robertson, and Keith van Rijsbergen told me that actually he came up with the explanation of the retrieval cost, which was then included in Steve's paper without mentioning that he had it from one of the reviewers. And so let's look at an example for this. So let's assume the system, for a given query, the system computes the following probabilities of relevance, 0.9, 0.8, and so on. And now we have a user who regards the first three documents. So that's one of the assumptions. You have a linear ranking, and user scans the documents linearly, does not jump, and stops at a certain point. And that for any stopping point, if you are following the PRP, for any stopping point, you get the optimum retrieval quality. Yeah. And we have to question what's the expected precision. Well, it's not 2012. That must have gotten somehow into the slide when my cursor was assumed to be somewhere else. Just ignore that. And what's the expected recall now for this cutoff point? But the precision, you can say, well, the expected precision is 0.9, 0.8, 0.5. So first document is relevant with probability 0.9, the second with probability 0.8, and the third with probability 0.5. And you regarded three documents overall, so the expected precision is 0.73. And you can also imagine that this is the highest precision you can get for three ranks, because if you swap any of these three documents with one of the following ones, then the sum here will get smaller, your precision will get lower. So you get the optimum precision here. And yeah, then recall. Oh, that's a bar missing. The sum of all documents here of all relevance probabilities in this case is 4, and then the recall, so that would be the expected total number of relevant documents in the whole collection. And then the recall again would be this 2.2 or so, yeah, 0.9 plus 0.8 plus 0.5, 2.2 relevant documents out of 4 would give you a recall of 0.55. And it's also obvious that that's the maximum recall you can reach for a cut of 3. Because again, if you swap one of these three documents with another one, you will get a smaller sum, and thus also a smaller record. So this means you get optimum retrieval performance here. Yes.
Partial conditions to this thing, right? Like if you have different information means that like if there were conditions to this somehow.
Yeah, of course there are certain preconditions. So for example, it does not address the issue of diversity ranking or that. So in principle, the idea is that user judges each document independent of all the other documents. So that's one of the additional assumptions, of course. So dependence between documents is not. So under certain assumptions, like also the independence and scanning and so on, then you can show that you achieve optimum performance. But it's always, you can always say, yeah, but this does not hold in reality, but just the statement as such, nevertheless, is universally valid. If you assume this and that, then you can conclude you have achieved optimal reality. Of course, you can try to formulate other models that are more appropriate or closer to reality, but the challenge always is to come up with something that is still universally valid. You might be able to find a solution that works fine for the few one or several test collections you're regarding, but the challenge in science is to make universally valid statements, because if you have results for a few collections, then someone turns up with another collection, asks you, will this also hold here? And then as an IR scientist, you say, well, you just have to perform an experiment in order to find out if it's also valid in this case. And that's what distinguishes IR from science, that we are not able to make predictions for new collections. We are not able to say how to make predictions. In showing your collection, I will derive certain parameters. But what we really need to do currently, run the experiment, and only then we are able to say something about the performance of our methods. So that's still one of the big challenges. Some years ago, we had a Dutch workshop on performance prediction, and we identified research areas and even wrote a project proposal involving Nicola and Martin, and who was the fourth? Pablo? Yeah. So, but unfortunately, we didn't get funded. So it's still a very open research issue. Okay, now I think it's time that.
What you said, I think it's very, very interesting that we propose a new method. The method performs remarkably well in one collection, and when you go to something, some other different collection, we have to retest, we have to verify.
Yeah.
But there are other areas of science where the same happens, right? For example, medicines. It's not always the same. When you find that some vaccine works, you have to test in with different ages, for example, child or device. You also have to make those adjustments.
Yeah, of course, but in medicine, they are able to specify the characteristics of their test sample and say, well, if someone else uses the same type of test sample, then the experiment should be reproducible. But in IR, how would you describe the features of your test sample that someone else's collection should also have in order to expect that we get the same result?
It's a characterization of the collection.
Yeah, that would be just the important parameters that we need to identify And that leads to, yeah, some kind of causality. If this, then that. But currently what we are doing is correlation. And that's the lowest form of understanding nature, observing certain correlations. But the next level is causality. You say if this and this and this, then you can reproduce our experiment. But this is still the step I have to go. Okay.
I was just going to say that although it's not the same distributed search, where you have the shards, you can characterize the shards, and you know that okay, for this type of query, that shard is more adequate, and then you just go to that shard. So the way you characterize subsets of the larger collection. Job Easter. He has a lot of work on it. It's very interesting. Challenge.
So all I'm saying is really good if from time to time you remember these basic features in order to understand, also to get the whole picture and put your own research into the right picture, maybe also get some ideas to improve your own work. Okay, but now we should have our coffee.